This is going to be really hard to fit into one video, but I'll give it a shot. Let's talk about Triplen Harmonics. This is my homemade three-phase Y system. I realized there's a lot going on. I wanted to hook up as much as I could, to show as much as I could. There are the 3 sine waves, and I'm powering these 3 incandescent light bulbs, A, B, and C, and I have meters hooked up to measure the current of A, B, and C. This one is measuring the neutral current. Now you can see all 3 legs are not 100% balanced. If they were, our neutral current would be 0. But this is acting just like a normal 3-phase Y system. If I turn one light bulb off, you can see the neutral current does raise. If I turn all 3 on, you can see it drops pretty close to 0, but again, they are not 100% balanced. These incandescent light bulbs are what we consider a linear load, meaning that the current follows the voltage applied. With linear loads, I'll turn these off, your neutral current would never exceed the current of one of the legs. So I have just A turned on. There is the current for A, so 164.8. Our neutral current, 165. You can see they're pretty close to each other. This neutral current would never exceed the actual current of the leg because this is a linear load. If you had 2, even with 2 on, so we're 165.6, this went up a little bit just because it's not perfectly balanced, but you can see the neutral current does not exceed any of the 3 legs. In fact, if they were all balanced, again, that would actually be 0. So what if we didn't have linear loads? LEDs are not linear loads. They do weird stuff in the camera because of the frame rate, but I've set these up similar to the incandescent light bulbs. So for A, B, and C, I've got 3 LEDs in series, and then with opposite polarity, another 3. So 6 LEDs per leg. I took this picture of the scope with all 3 legs hooked up on the load side of the LEDs. You can see that they're not a linear load. If you follow one of those sine waves, you see how it's offset because the current does not follow the voltage applied. But what does that mean for our neutral current? Well, again, we have leg A, B, and C. This is our current on each 3 legs, but notice on our neutral current now, it is higher than any of the 3 legs. Also notice the frequency, 180 hertz. This is caused by something called Triplen Harmonics. So here's my 3 fundamental sine waves. You can see they look all nice. Notice this distorted one. I'm gonna turn off some of these channels just so it's a little bit easier to look at. Let's follow this yellow one. So from here, this 0 point, down to the negative peak, positive peak, back to 0. That's one cycle of this sine wave. But let's follow this other one. This is our Triplen Harmonic neutral current. So we have 1, 2, 3 cycles of that compared to the 1. Our fundamental sine waves are 120 degrees apart. So if we had linear loads and the same load on all 3 legs, they would cancel out and our neutral current would be 0. But because of this Triplen Harmonics, these third harmonics, it's 120 times 3, so 360 degrees, putting all 3 harmonic currents in phase. So they add rather than cancel.